Welcome to all in the new lecture, or you can say that the first lecture of this new year. First of all, I want to say that I wish you a very happy new year this 2021, and may I pray for that this year will be good and healthy for everyone. So now let's start our the today's lecture. So here we start the next unit that is on first topic of that is mathematical induction. So in this lecture we cover the first part of mathematical induction. Here I will tell you that what is the mathematical induction, where we use the mathematical induction, how we use the mathematical induction method, and in the second part we will take some other examples of this. So let's start today's lecture. So, first of all, what is mathematical induction? Actually, there are two aspects to mathematics. What is that? That are discovery and proof. Means in mathematics, we have always the two aspects, that is discovery and proof. So, both are equal importance actually. What is the meaning of discovery? Discovery means you have an conjecture like that, or you can say that if you have suppose any equation, you know that the equation, any differential equation or any equation you have, so that is your and you use their parameters, so that is your discovery, means this equation. But what is if you but how you can say that this equation is right or wrong? Means without proof you can't say that the given equation or the equation which you use, that is right or wrong. So both things are important here in mathematics, that is discovery and proof. So we must discover something before we can attempt to prove it, because before anything we have to prove, but we need the some equations, means we have some discover, after that we prove this, right? And if suppose we have some discover, but when we say that this is true, once it has been proved, then we can say that yeah, this is right. Okay. So, in this section, we examine the relationship between these two key components of the mathematics more closely. What are these? Conjecture and proof. So, what is that? Let's try example. Actually, I think you don't understand what is that. Actually, just say that we take a simple example. Okay, so I think you can understand with this. So here we add some more odd numbers, right? Suppose first odd number at 1 equal to 1. When what is the next odd number of after the 1? 3. So 1 plus 3 is you will get 4. And next odd number is 5. So 1 plus 3 plus 5, that is sum is 9. After that, the next odd number after 5 is 7. So the sum of first odd numbers, 1 plus 3 plus 5 plus 7, when you sum it, that is equal to 16. And after the 7 the odd number is 9, so the sum of 1 plus 3 plus 5 plus 7 plus 9, that is 25. So you see this, what you see that in the right side, which type of equations you will get here? 1, 4, 9, 16, 25. Can you assumption that what is that? 1, 4, 9, 16, 25. Yes, these are the perfect squares, right? How? See here, the sum, when we sum the first odd number, the first odd number sum is 1 square, right? First two odd numbers mean 1 plus 3, but you will get 4, and 4 is it means that 2 square. Now first three odd numbers, 1 plus 3 plus 5, what you will get? 9, and 9 is a s- 3 square, right? So these all are the perfect squares. When we add the first four numbers, so we will get the 16, and 16 is the 4 square. So like that you have the all are the perfect squares, right? So So these are naturally of the question arises, what is that? Is it true for every natural number n the sum of first and odd numbers is n square? Means after the doing these five, if you add some five odd numbers and you will get the sequence is like that: 1 square, 2 square, 3 square, 4 square, 5 square. So after this, can you say this that all natural numbers for every, these are the natural numbers, right? 1, 2, 3, 4, 5. So we can we say that for every natural number and the sum of first odd numbers is n square? Can you say this? Yes. It is, or you can say that this is probably true. Means if suppose we do only five terms add, after adding we get this sequence, so can you say that after a long term if you added odd terms then you will get this sequence? So let's try here. So like here, if we take says suppose that 6, 7, 8, 9, 10, if we add these numbers, so obviously we will get like that the power of n square. But suppose at this point we feel quite sure that this is always true. If we will get suppose 6, 7, 8, 9, at 10 terms we add, and we will get this type of structure. So it is make a conjecture. Means when you try this, so it's make a conjecture. What is the conjecture? That the sum of first n odd numbers is n square, we can say this. But what is that? This is a conjecture because it gives only this the sum of first, but you can't till now you haven't proved it that. Okay. So now and what is the in mathematically, how can you write this? The sum of first and odd numbers is n square. So we know that the nth odd number is 2n minus 1, right? So we can write this 1 plus 3 plus 5 means odd numbers, plus last term is 2n minus 1. The odd number sum is equal to n square, right? So by mathematically you can say this. So this is form a conjecture, right? This says that the sum of odd numbers, first odd numbers, is n square. So now it's important to realize that this is still a conjecture, right? We can't conclude that by checking a finite number of cases that a properly it is true for all numbers, because here we take some numbers and add some odd numbers and conclude with this that it will be n square. But can you verify this that if we take some numbers and can we conclude that this will be n square? Only if we take some finite numbers then we can conclude that it will be n square. Suppose we have to take the infinitely many times, we can take the many numbers. So how can you say that this will be true? Maybe for any number in till infinity you have any number is like that which is not the square. So how can so then what will you do? So let's see here. Suppose someone says that tell us he has added up first trillion odd numbers, because we have the infinite numbers, so many numbers are there. Suppose one says that first trillion numbers odd numbers and find that do not add up to 1 trillion squared. Suppose one person says that he add the first trillion odd numbers and 1 trillion squared. He says that 1 tree, if we add 1 trillion numbers, then that square is not the squares, that number is not the any square. So what you do, what you tell this person? What it would be? Suppose you say that no, I am sure it is true. Because why? Because I checked the first five cases. You say this? No. If you say this, that is a very silly type of this says that no, I have checked the five times, so it will be true. It is not like that. That 1 trillion squared is 1 trillion add sum of this not the squared, right? No. So you what you do now? So you now first you add the first five terms, now you add one by one, more and more terms, right? So for this you have to take paper and pen and adding the numbers and find the results. But I think it will be a very, very, very big task that you add the whole natural odd numbers up to infinity, right? So, what you do for this? Uh, for this to prove, we use our the proof. So it here actually in this step, here we realize that the power of mathematical proof means if mathematically we can prove this, that this thing is right. So you can say that yeah, all natural numbers or natural numbers sum is n square. So let's see here. So after the proof, you can say that yeah, argument that demonstrate the truth of statement beyond doubt, right? Means so what you can say that this is the method is mathematical induction. So by mathematical induction method, we can say that any statement which we make that is true after proving that it is true or not, right? So let's see how it will work this mathematical induction method. So in this method, suppose we have a statement that says something about all natural numbers n. So first we suppose that that statement is p, right? So now p means may we say that a statement for every natural number n, the sum of first and odd numbers is n square. So first we say that this term is our capital P. Now uh, what is that this statement actually about all natural numbers, so it contains infinitely many statements like that. Suppose we say that p1 p2 means p1 what is the meaning of p1? P1 is that the sum of first of one odd numbers is 1 square. P2 means is that the sum of first two odd numbers is 2 square, and p3 meaning is that the sum of first three odd numbers is 3 square, up to like that. Now, how can you prove all these statements at once? At once, how can you prove this? So here we use the mathematical induction. That is a very clever way of doing so. Now, the crux of the idea is that suppose we can prove that whenever one of these statements is true, then one following it in the list is also true. That is, for every k, if pk is true, then pk plus 1 is true. So this is called the induction step. What step? This step. If pk is true, then pk plus 1 is true. So this step is called the induction step, since it leads us from the truth of one statement to the next. Means if this is true and we show that we if we show that this is also true for pk plus 1, so our method is completed, right? Now, first for this, suppose that we can prove that P1 is true. So if we have first we have to prove that P1 is true. Now the induction step now leads us through the following chain of statements. What is that? P1 is true, so P2 is true. P2 is true. This is the uh, induction step. P3 is true, so P4 is true, up to like that. So we see that if both the induction step and P1 are proved, then statement P is proved for all n. So this is the uh, way of doing this. So now we see that what is the summary of this method. So see, check here, principle of mathematical induction. For each natural number n, let Pn be a statement depending on n, right? So, suppose that these conditions are satisfied. What? First step. What will be our first step? First step is this, in this method, that P1 is true. Means any statement it is given in the form of n, we have to check that for n equal to 1 it is true or not. So first step is we have to show that P1 is true. After that, for every natural number k, if pk is true, then pk plus 1 is true. So now we say that Pn is true for all natural numbers n. So this is the method of mathematical induction method. So now how to apply this principle. So there are, what are the steps? There are two steps. First step is prove that p1 is true, and second step is that assume that pk is true. Means here we in the second step we have not to prove that pk, this is for pk is true. We have to assume here only that yeah, pk is true for this, and using this pk value we have to prove that pk plus 1 is true. So this is the induction hypothesis. So uh, what is that? I told you that we have to not prove that pk is true. Okay, we have to assume only that yeah, it is true for pk. Then we have to prove this for pk plus 1. So the assumption pk is true is called the induction hypothesis. We now use mathematical induction to prove that the conjecture we made at the beginning of this section is true, right? So let's see here. After we take an example and to you clarify that how can work this method. So first we take here the all natural odd numbers sum is n square. So first what will be our first thing? First thing is that we assume that this statement is our Pn. N means because this is the nth term, so we denote it by Pn. Now what is the first step? First step is we have to show that P1 is true. P1 is true, it means that we have to put n equal to 1 here in this equation and get uh, right left hand side equal to right side, right? So what is the first term of left side? That is 1. So here we put n equal to 1. So n equal to 1 we put here, that is 1 square, and 1 square is equal to 1. So we say simply that P1 is true, right? Okay, now the step 2. So what is the step 2? In step 2 we have to assume that pk is true. So we have to consider it that yeah, it is true for pk. So our induction hypothesis is we have to put here only simply n equal to p. So 1 plus 3 plus 5 up to 2k minus 1 equal to k square. So simply just we have to put k in place of n, and we assume that yeah, it is true for pk, right? Now next step is that we want to use this pk to show that pk plus 1 is true, right? So now we have to put k plus 1 in place of n. So 1 plus 3k, what we have? 2k minus 1, 2n minus 1. So when you put n, k plus 1 in place of k, so you will get like that 2k plus 1 minus 1. This is n, 2n minus 1. And what will be the earlier term for this? The earlier term will be 2, because this is k plus 1, like k plus 1 term. So before term will be 2k minus 1, like that, equal to n square, and n is here k plus 1, so k plus 1 square. So when we put directly n equal to k plus 1, so we will get this type of equation, right? Now here you see that pk plus 1 by substituting n equal to k plus 1, right? So now we start with the left side. Now we take the left side, and after using the induction hypothesis, what is the induction hypothesis? pk. So we have to take the left side and solve the left side by assuming and by considering, by using the pk, and prove that the right part. If we get the right part after solving this, we get the right part is k plus 1 ka whole square. So we say that yeah, it is true for pk plus 1, right? Okay, so now what is our left side? That is 2k minus 1, 2k plus 1 minus 1. Now what we do here? Here we group the first k terms. So what will be our first k terms? Up to here these are the first k terms, because this is k plus 1 term. So here this is up to kth term r, right? Now after that, this is which I told that kth term, that is k square. By our induction hypothesis, our value of pk. What is our value of pk? The sum of our numbers is equal to k square. So we put here all these terms k square, and this is. Now after this, 2 we multiply 2 here, means we use the distributive property, that is says 2k plus 2 minus 1. Now after solving this, we get k square plus 2k, and this is plus 1. Now what is this k square plus 2k plus 1? You can say that k plus 1 whole square. And what is it? It is our right hand side, right? So we can say that yeah, this is true for pk plus 1. So now our induction step is completed now. So after this, we conclude that yes, having solved step 1 and step 2, we conclude that by the principle of mathematical induction, what we can say that yes, Pn is true for all natural numbers n. Clear? Means in mathematics we have the two things. First is conjecture and proof. Conjecture means if you have some parameters, then you can make a equation, but after proving this, you can say that yeah, this is true. So we prove this by mathematical induction method. We can prove this and sure about that yeah, this is true. Clear? Okay, so now today's lecture is completed now. Thank you. Be happy and be healthy.